a great article, go to share the link, and realize it's a massive, endless wall of gibberish. But then you paste that giant block of text into a URL shortener, click a button, and instantly it becomes 6 neat, tidy letters. How exactly does that happen? It seems like the computer somehow compressed hundreds of characters of text into just 6 tiny letters. But the actual reality is quite different. This process relies on a massive, highly organized digital filing system working behind the scenes. To understand how they work, imagine the internet as a colossal, hyper-efficient digital library. That massive, ugly original link you wanted to share is like a giant, incredibly heavy encyclopedia. It's way too cumbersome to carry around. So you hand this heavy encyclopedia to the librarian at the front desk. They take it from you, carry it off, and securely file it away on a specific shelf in the massive back room. In return, the librarian hands you a tiny claim ticket with a short, unique ID code stamped on it. The short link you share online serves as the locator ticket for where the original site lives in the library. Now, think about what happens the moment a friend clicks that tiny link you sent them. This flowchart maps exactly what is happening in the background. Clicking the link is the digital equivalent of your friend walking right up to the librarian and handing over that tiny claim ticket. The librarian reads the ticket, instantly fetches the correct book from the exact shelf, and hands it directly to your friend. In the software world, we call this handoff a server redirect. That seamless experience of clicking a link and landing on a web page is actually a rapid, invisible database lookup happening in a fraction of a millisecond. But here is where we run into a scale problem. How does the librarian organize billions of individual web pages without running out of claim tickets? If the library just used standard numbers, counting ticket 1, 2, 3, and so on, the tickets would eventually get incredibly long to accommodate billions of web pages. We'd be back to the original problem of ugly links. Engineers solved the scale problem using an expanded alphabet called base 62, numbers, lowercase, and uppercase letters. Giving each slot 62 options means a 6-symbol ticket generates over 56 billion unique codes. Base 62 encoding allows the internet to map an almost infinite number of links into a very finite, tiny space. Let's stress test this system. Imagine a massive celebrity posts a short link to a new product. Suddenly, 10 million people rush the front desk at the exact same second, demanding the exact same book. If the librarian has to run all the way to the back shelf to fetch the original book for every single person individually, the entire system will be overwhelmed and crash. System engineers protect databases from this exact scenario using a concept called caching. Instead of running to the back shelves 10 million times, the librarian simply keeps a massive stack of that specific viral book right at the front reception desk. Caches save modern websites from crashing by handling the most popular, high-traffic requests right at the front desk, bypassing the slower main database. Now that we have all the pieces, we can drop the library story and map these ideas directly onto a real-world software architecture. This diagram shows the translation. The heavy book maps to the long URL, and the claim ticket becomes our base 62 short link. The librarian and shelves translate into a server and database. Finally, the front desk acts as a cache, intercepting requests for viral links. URL shorteners rely on precise mapping, routing, and scalable storage architecture, rather than complex compression algorithms. So the next time you click on a tiny 6-letter link, you can picture the invisible, hyper-fast lookup happening beneath your screen. Mastering these simple, everyday components, databases, encoding alphabets, and caching layers, is the first step to understanding how all massive software systems are built. In our next episode, we'll take these building blocks even further and look at how streaming giants manage to beam massive 4K movies directly to your television without buffering. The internet operates through these systems of brilliant, perfectly scaled organization.